Again, good morning, everyone. So, later on in this course, we will be looking into graph neural networks. And so, how many of you know neural networks? I think there was a survey done, right? A lot of people know neural networks. Okay. Okay. A lot of you know neural networks. So, for them, they can take a quick nap or but for others so uh, so because unless you know neural networks, GNN won't be easy for you to understand. So today we will have a brief introduction to neural networks. Okay, so at one level you can think of neural networks, so there is lot of hype on neural networks, but you can think of it as a function that takes an input x and computes an output y. So what sets it apart from, say, y equal to sine x or other kind of function is the manner in which it is constructed. Okay, so because of the complex nature of the neural network, you can do magical things using this neural network. It is composed of many very simple elements that together somehow manage to perform very complex tasks. Okay. And the term neural itself derives from the fact that simple units that are network to compose a model are conceptually similar to neurons in our brains. So in our brains also, each neuron is a simple element, but they combine together to do really, really complex start. And the initial um, inspiration for neural network was, of course, our human brain. Okay. So what happens is neurons in our cerebral cortex are connected by axons, and when a neuron fires, it's connected to when enough of the input signals are activated. So if you have a neuron and it has lot of input signals. If they get fired, then the neuron get activated. Okay. So at the individual neuron level, it's a very simple thing. So you have some inputs which, when get activated, the neuron gets activated. But this things actually use the learning behavior, because there are actually in our brains billions of neuron, each with thousands of connections. Okay. So the first artificial neuron, so that was done in 1943, well before the computers. Okay, so what it says that we have a neuron C, which fires if more than n input connections are active. So depending on the number of connections from each input neuron and how it is activated, we can create a AND gate or a OR gate, things that you have studied already in your initial undergraduate courses. Okay. Okay. So in 1957, we developed something called the linear threshold unit. So where given the inputs, it could add the weights of the input in various ways, and you can sum up those products. And if the sum is greater than 0, then you can say that the output of this neuron is 1. Okay. So that was the basic linear threshold unit. And then Frank Rosenblatt, he created what it's called a perceptron. So again, here we are trying to mimic the human brain, where there are multiple neurons together. So the perceptron is a layer of linear threshold unit. A perceptron can learn by looking into the weights, and that can lead to some behavior during the training. It can learn the weights and then it can change the weights so that you can learn on this. Okay, so this also, as I said, was biological basis. So cells that fired together, wired together. Okay, so basically, what you have is you have a set of inputs, and then for each input there is a weight on how much it contributes to that output function, and then you have a sum of it, and you add a bias to this. We will talk about bias more, and then you sum this up to get a sum of those weights. So, and those, so for example, the sum would be W1 into X1 plus W2 into X2 plus W3 into X3 plus Wn into Xn, and so on. And then we have the sum, and then we have some function which, given the sum, it will determine the output. Okay, so you have the sum of the things together, you add a bias to that to control the overall function, and then so we have a activation function that will, depending on the value that you get, the value z that you get, it will try to find the output. Okay, that is how this perceptron occurs. Okay, so the activation function, so what the activation function does, it defines the output of a node given an input or a set of inputs. Okay, so you have first summed it up, and then the activation function decides whether the neuron should be activated, whether it should be a plus or it should not get activated. And there are various kind of activation functions you can do. The first is just a step function. So it's very easy. If x equal to 1, if x is greater than or equal to 0, and if x is equal to 0, if it is less than 0. Okay. So that is a very simple activation function. But what is much more common is a softmax function. Okay, so it scales numbers or logits into probabilities. So here you have a probability that you have, and the probability values is determined by the output that you get. So what happens is the output may be a number. From there you have a probability distribution using this function. Okay, so this is a very common activation function that is used. Okay, another is the sigmoid function, which takes any real value as input and output in the range 0 to 1, and larger the input, more positive, the closer the output value would be to 1. Okay, and smaller value would be 0. So this is another common function that you use. So here you can have values between 0 to 1. Okay, and then there is ReLU function. It's a non-linear function or piecewise linear that will output the input directly if it is positive. So if it is the output is positive, then it will output that, but otherwise it will have 0. So these activation functions are important. So given the value that you get, it will determine whether the neuron will fire or not. Okay. So the perceptron, you can, depending on what the task at hand. So for example, if it is a classification task where you are trying to say whether this mail is a spam mail or not, then the output can be a Boolean function. So you have the input, so you have utilized various kind of features of the data to determine whether that mail is a spam mail or not, or you have done some transaction, and based on that you want to say whether that the transaction is a legitimate transaction or not. So here it's a two things. You are either saying that it's a legitimate or it is not a legitimate, it's a spam mail or not a spam mail. So its output is a Boolean. So based on the values that you get, you can have one of those functions to determine whether the output is Boolean or not. Okay, so that is one case. So for example, if you are using this neural network for a classification task, then you can do that. Okay, or the output can also be a real number. Okay, so for example, in sigmoid you can get a real number, and real number would be useful for a regression kind of task where you are trying to say that what would be the value of something at the end of you are trying to predict a value. Okay, and the values can be a real number. So for some kind of regression kind of task, you can have output real, and then you can utilize a perceptron to do that. Okay, so the when it gets interesting is that besides the input and the output layer, just like our brain, you have lot of hidden layers. So, and this is a multi-layer perceptron. So it makes it much more complex kind of function where you have the input layer, you have the output layer, but you have lots of hidden layers. So and each of these hidden layer is trying to calculate some values and then passing on to the next layer. And as you have this kind of uh, multi-layer perceptron with number of hidden layers, you can do really complex functions. Okay. How this multi-layer perceptron works is that the computation of MLP is performed sequentially. So from the first input layer, you calculate using the weights the first hidden layer. From the first hidden layer, you calculate the second hidden layer, and so on. And finally, you get the output layer. So the multi-layer perceptron is the modern day neural network, the initial neural networks that were created that became popular were these multi-layer perceptrons, and even now they are utilized for various functions. So when you are studying about graph neural network, you will see that as part of it, for some of the tasks you can use a MLP also in a GNN. Okay. So what happens is each layer of this multi-layer perceptron combines a linear transformation and non-linearity. So given a layer, so what it does, the output of the layer, so the output of the L+1 layer would be the outputs from the Lth layer multiplied by the weights in that layer. You add a bias term. So adding the bias term provides more flexibility and more generalization. And so this, when you add these terms, the weights into the input layer plus the bias, it is a linear kind of combination. And then you will add a nonlinearity to that using an activation function to get the final output. So we look why we add the nonlinearity, we will look into a little later. Okay. So suppose we have a two-dimensional with entries x1 and x2. We can combine the two with one hidden layer to get the output dimension. So this is the basic way multi-layer perceptron works. It has the input, it multiplies it with the weight, and then it gets to the next layer. The next layer gets to the next layer, and so on. Okay, so that is how it will work. So, but then, so suppose you have a task at hand. Okay, so for example, you have a classification task I told about, for example, whether a mail is spam or not, and so on. So what you want to do, you have given a lot of features about the mails, a lot of features about the transaction. So you calculate the various values. In the middle, you have some hidden layers. You calculate the various layers. You put the weights in, and you calculate the output, and you get the output. And output, so if you have 1,000 mails, it will say, okay, these mails, 70 of them are spam, the others are good. And then you have some, so there are, you have the, for the training data, you will have the value whether they're actually correct or not. And then once you have those training data, you know, okay, this is the kind of training that we have done, and this is the kind of errors we are getting. And then you try to train the multi-layer perceptron. And so what you, in the training, what happens is that the weights that you have for each layer, those are the weights that get to be adjusted, so that the more and more you try to get correct answer. So what is meant by training a neural network is trying to adjust the weights, trying to adjust the biases. So we talked about these weights that are there. So we try to adjust the weights so that as you change the weights during each training set, the final output, you are the assumption is that the goal is that we will get more and more correct data. Okay. So the these parameters, so as you train, so the parameters get tuned, and finally with that tuning, what happens is that you get more and more correct data. So training the network is the process of learning these values, because when you start, you put some random values for these weights, but as you go forward, what you try to do, you train the network so that you can learn the weights better. Okay, so the network performs the task correctly. The actual training process is an iterative process. So you try to you start with some random weights, you try to then use the weights, you try to get the final output, and then based on the output that you get, you again go and adjust the weights going forward and try to do that in an iterative way until you get some good result. Finally, you would try to see so that the network outputs mostly correct results. Okay. So there are so the training, as I said, is an iterative process. The first is a forward propagation. In the forward propagation, what happens is that you use the weights that you have, you multiply it with the input, and you get the hidden layers. And from the hidden layers, you get the final output, and the final output will give you whether that mail is a spam or not, and you have that. And so that is the forward propagation. We are going from the input to the output, and from the output we are getting the final result whether that mail is spam or not. And then so once you have the first one iteration done, you calculate a loss function. So what is the loss function? The loss function will tell you that how many, so for example, out of the 1,000 training data, maybe 80 of it is wrong. Okay, so the loss function is used to compare the target and the predicted output values. Okay, how well the neural network has done. So if you feel the your output is very good, you have already got say 99% correct, then you are done with the training. So that is the thing. So from the loss function, you know, okay, I have 99% correct, I'm satisfied. But sometimes what happens, it would be maybe 70% correct. And then you have to tune the weights again and again. And for that, what we have is a back propagation. So what back propagation does is that for each training instance, we compute backward from the output. For each of the layer, we will say, okay, can we adjust the weights a little more so that the result would be better. Okay, so it involves taking the error rate of the forward propagation and feeding the loss backwards through the neural network layers to fine tune the weights. So that is what back propagation does, and you do it again and again. Forward propagation, calculate the loss function, back propagation to adjust the weights, and you go on doing this iteratively until you get good values for the final result. Okay. So this is the artificial neural network, and so this was the initial model of neural network that was created. So here what is assumed is that we have all the data that you have in columns. Okay, so x1, x2, x3, these are the various features. So for example, for a mail, it can be who is sending the mail, from which domain it is coming. So all the features are listed as columns. Okay, and from those we try to do the calculation. So that is very good for a lot of tasks. So for example, for finding out a fraudulent transaction, for finding out fraudulent emails and things like that, you can adjust all the data in columns. But you cannot do that for example, images, for machine translation, for sentence classification. And so what happens is we have more and more new kind of models that are getting created, so that the input is different for those, and for that you can create different kind of models. Okay, so especially for this example of a image, right? So for example, if you have a stop sign in a picture that you try to find out, okay, that you cannot put it as features. Okay, so that is the limitation of ANN that you have, and therefore, so for example, we'll look into why this model of simple model that you have, where all the features are mentioned in columns, does not work, or graphs also. Okay. But before we go into that, let us again go back to this neural network problem where we have this training that we are doing. Okay, so we can consider this to be an optimization problem. Okay, so we are given an input X, and the goal is to predict label Y. Okay, and label can be either true or false, or it can be numbers and things like that. And inputs can be vectors of real numbers, or it can be other kind of things. So for example, for convolutional neural networks, which are images, it can be matrices, or it can be for if you are doing text classification or natural language prediction, it can be sequence of natural language, or it can be graphs that we will look into. And whole of GNN, what it will study is how you can input the graph in an effective way in a neural network. Okay, but so that is the task at hand, how you give the input. But the overall problem of neural network can be is nothing more than an optimization problem. Okay, so you have formulate the task as an optimization problem, where you have a set of parameters and you try to have this objective function, and you will try to optimize that function. Okay, so this set of parameters can have lot of things. It can have class scalars, vectors, matrices, and so on. And the loss function can be of various kinds. So for example, you can have it as y minus fx, where y is the actual value, fx is the value that is you got from the neural network. You try to have the loss function and you try to minimize that. Okay. So in a classification task that I told you about, so if it is a binary classification, you will have only two classes. You will say that it one class is 0, the other class is 1. But classification can also be of multiple things. So for example, you are given an image and you have to say whether it's a cat or a dog or a tiger or a rabbit and things like that. So for example, if there is a 5-way classification, then you can represent it as this is called a one-hot encoding. So if you, for example, the first one says that it's a cat, the second one says it's a dog, third one says it's a rat, and suppose we know that this is a picture of a rat, then the third one would be 1, others would be 0. Okay, that is how you represent y. So that is the label, the actual categorical value that of the correct thing. And suppose your neural network has said it was not sure, so it has used a probability distribution. It says with 0.1 probability, I'm thinking that it's a cat. With 0.3, I'm thinking it's a dog. With 0.4, I'm thinking it's a rat, and so on. So that is the output that is that you get from the neural network. Then what you do, you try to have a cross entropy. So this is, it tries to see what is the exact error that you are getting. Okay, the lower, and so if the actual value you actually get 1 and zeros, then you will get a perfect 0 score, and your so loss would be 0. But other than that, there would be a loss that you get, and so this loss is calculated, and the training set. So once you have done the training, you will get a loss, and if the loss is high, then you will try to again adjust the weight. Okay. So how to optimize it? So you have to do what is something called a gradient descent. Okay, gradient is the directional derivative in the direction of the largest increase. So for example, if you consider this, so this function fx to be a function, then the function will have a minimum point. So that is the place where you want to get. And so how you get, so this is the function of the cost with the thing. So what you want to do is the cost you want to minimize. You want to get to the minimum cost at the bottom of the thing. And suppose actually based on the initial weight that you have got to the, once you have done the loss function, you are at the top. So the goal of gradient descent is so this is a step that you do in during backward propagation. From the initial weights, if you get a loss function, you will try to see how you can reach the point where there is a minimum cost. So for that, you do this incremental step of coming down. So you try to adjust the weight so that you can go down and down in this. So gradient descent, it iteratively calculates the next point using the gradient of the current position, scales it by a learning rate, and subtracts the obtained value from the correct position. Okay, so it tries to go down this gradient so that you can come to the lowest minimum cost function. Okay. So it's again, so that is a iterative algorithm repeatedly updates the weight in the opposite direction of the gradient. So what you will try to do is that you have the weights and you will try to adjust the weight so that your loss function decreases and you come down. And so another important parameter is a learning rate. So how much, so suppose you are at the initial weight and then you see these arrows. Those arrows determine how much you should adjust the weight to come down. Okay. So what is the disadvantage if you have very small of these arrows? Then it will take a long time to come to the bottom, right? Because if you have very minute adjustment, then it will take maybe 100, 200, 1,000 steps to come to the objective function. So now instead of that, suppose you say, and the learning rate controls this, how much you are going down. Okay. So, but what is the disadvantage if you decide, oh, I will take a very large learning rate, so that I can immediately in one step come down to the minimum cost. So, what would be the problem if you have a very exactly. So, what you can do instead of missing the optimal point, you can go to that side. Okay, so that is the problem that will happen if you have a very high learning rate. So you should have a optimum value of this learning rate. So you don't miss the optimum, you don't go to the other side. So it's a very fine tuning kind of thing. So so what is the thing that you do in this neural network, this training this neural network and fine tuning all these parameter, that is one of the uh, key things that you have to do. So the ideal termination condition would be zero gradient. So we will stop training if we can reach the point of zero gradient. Okay, so that then after you do the training, it won't improve the performance anymore. Okay. So the gradient descent, so you go step by step, you come down and you try to reach that. And so that if you use this gradient descent, obviously you can get the correct result, but it may take a long time. And therefore, people have come up with a solution called the stochastic gradient descent. Okay. So the problem with gradient descent is the exact gradient requires computing this for the entire data set. So for the, suppose you have thousands of values in the data set, for each of them you have to do this calculation of this gradient descent for all the points in the data set. Okay. And so for example, for a modern data sets, you have billions of data points, right? So for example, if you are doing a language tuning, right, it will have billions of data points. So therefore, it becomes extremely expensive to do the gradient descent. So what you do, instead of doing it for the whole batch, whole billion thing, you take a mini batch. So mini batch may have 1,000 instead of billions, and you do this gradient descent for that 1,000. Okay. So what it does, it addresses the computational inefficiency of traditional gradient descent method. Okay, instead of using the entire data set, it at each sample you do not use the same batch. Each time you teach a different batch, and you try to utilize that. So first time you take 1,000, the second time you take some other 1,000. You randomly select different batch and try to utilize that for your calculation. And therefore it is called stochastic. Stochastic means it is random. Okay, the random selection of, and this random selection also introduces randomness in the optimization process. Okay, so it is, so the stochastic descent is much more computationally effective. Okay. So stochastic gradient descent, it will have some other parameters that you will need. It's that other parameters. So for example, batch size, number of actual data points that you use. So for example, from the billion data, are you using 1,000 or are you using 10,000? So batch size is an important hyperparameter to use. Iteration, so which step of the HGD you are doing, and one full pass of the overall data set is called the epoch. Okay. So that it is an unbiased estimator of the full gradient descent, but so you can get much more performance improvement using SGD. So therefore, so what happens is the neural network. So the objective is you can write it as an optimization problem where you are trying to minimize the loss given the actual data that you have and the data that you have calculated. So and this function f can be very complex. So it in a multi-layer perceptron with multiple layers, fx can be very complex, but the overall goal is to minimize. You can think of it just as an optimization problem. So to start with, we consider a linear function, fx equal to wx, and if f returns a scalar, then fx is a learnable, w is a learnable vector, or it can also be a weight matrix. Okay, and then in back propagation, what you do, so you have a chain of so you have each of these layers. So fx can be w2 into w1x. So because what you have, each of these layers will have a weight calculated with it. Okay. So in high school calculus, you know about this chain rule, dz dx equal to dz dy dx. So what you are doing is taking advantage of the chain rule. In each of the step, what you are trying to do, you are trying to minimize the gradient for. So first you will try to minimize the gradient for dz dy, then you will try to minimize the gradient for dy dx, and so on. So the back propagation uses the chain rule to propagate the gradients of intermediate steps and finally obtain the gradient of the overall loss function. So that is how back propagation works. Okay. So for a two-layer, so you have W2, W1x. So to calculate the loss, what you do, you first do for the first layer. So for W2, you first try to reduce it, then you try to do that for W1 and so on. Okay. So first step is a forward propagation. From x, you calculate, you multiply x with w1 to get h. Then you multiply those with w2 to get g, and from there you finally get the loss. And so in the forward propagation, you move from x to the output, and in the backward propagation, you move from the back from w2 w1 to df w2 and so on. Okay. So this is how, at a high level, how a neural network works. Okay. So now, so as you see, so if we just have these layers where we say that fx h1 is w1x and so g x equal to w2x. So these are linear functions. So you are only using linearity. So but why that is not good is that because then the function becomes, the kind of calculation, kind of values it can get is very limited, because linear function can do only simple calculation, but you want neural networks to do complex functions as well. And therefore what you do, you add this non-linearity. So once you have fx equal to w2 w1 x, you add a non-linearity to that, and so the non-linearity allows neural network to develop complex representation and functions based on the input. Okay, so if it is just a simple linear function, you cannot add complexity. So therefore you use non-linearity. You can, we talked about the activation function, you can add the ReLU activation function or the sigmoid activation function. Those are very common, and what it does, it's given a linear function, it will add non-linearity to that, so that the final function that you have becomes much more complex. Okay. So that in summary is how neural network works, and then you so you have the objective is to minimize this loss function, and so it can be a simple linear layer, so multi-layer perceptron and so on, or it can be so overall everyone has the same underlying objective, and then but how this function is created, this different neural networks will have different ways. The CNN will have a different way and so on. So you have the sample of mini batch of input x, you have the forward propagation, and then you have the backward propagation which goes back, and then you have the SGT to find the optimization. So that is in a summary how a neural network will work. But as I said, so generally for the traditional how neural network started, you have a column of features that you use, but that in many cases is not useful. So you just a column of features won't work. So for example, in convolution neural networks, so that was inspired by images. Okay, how you do images. So given an image, you cannot directly say that I will have a column of features. So there may be some features that are you can put it in columns, but for a large image where you want to, so for example, find for a cat, you want to find its tail, you want to find that eye. So finding the feature just by a column is not good. So, and our visual cortex, which is used for finding images, also doesn't work that way. Okay. So how our visual cortex works is that for each part of an image that we see, we have our cortex looking into those parts. Okay, and so once we look into small parts of an image, then we combine them together to get higher layers. Okay, and so uh, and then for color images, we have extra layers for red, green, blue, and so on. And so the convolution neural network was built for that purpose. So for example, we want to see the stop sign. If we just take a columnar feature, finding the stop sign would be very difficult, because how do we represent the stop sign from a large image? Okay, and so how do we our brain see the stop sign? It looks for edges, it picks up these edges for these stop signs by looking into create for a large image. It will break it up into smaller parts, and then it will look for the edge of the stop sign and so on, so that, and then it will pass it into a higher layer. Okay, so it will look into break it up into smaller parts, and then it will pass it on to a brain, and your brain know that that this is how a stop sign will work. Okay, and so this uh, goes on and on, and then you will understand this is a stop sign, and if you are driving a car, it will stop. So what CNN does is that uh, you will have a multi-layer perceptron at the end, but how the features get formed is from an input image. It will take smaller parts of the image, and then for each of the small parts, it will try to find features, and then it will try to know each of the, for a large image, for each of the small part what it is doing, and then it will calculate that and then do the final classification that this is a stop sign. Okay, so what, given a large image, it will create small uh, f- uh, 2 by 2 kind of kernels, and then it will see what are the values in that places. So for example, for this small part, it is 0, 1, 3, 4, and then it will try to see do a maximum pooling. So it will try to multiply these with the small things, so and then it will get the values for that, and then it will use these pooling layers for small things, and then try to figure out what is the feature of these images. Okay, and from there it will create the final fully connected layer that will be utilized for creating the image. Okay, so CNN is very good for images, and then the new thing, the transformer architecture, is very good for natural language, but those are very tuned. So CNN is very tuned for images. Transformer architecture is very good for sequence of text. Okay, so depending on the images, the text, what you do is you first do some pre-processing so that those can be represented as a multi-layer perceptron. Okay, and so from those images or the text, you try to create features that will be used for the multi-layer perceptron, and finally you have the output layer. So people have created different models for different kind of input data, but none of these models are good for graphs. Okay, so graph, what is a graph? Is a network structure, and it is of arbitrary size and complex topological structure, as you all know. And so this network structure is not a image or not a text. So both in images and in text, you have a fixed node ordering or reference point. You know that the image, if you start from the left, you can go from the left, you can do one row, then you come to the next row. And therefore, for each of them, you can create smaller kernels and try to figure out what is there, what are the features in that. Similarly, for text, what you can do, you go from text from the left to the right, unless it's some other language, and then you try to calculate the features. So initially what people did, they tried to utilize this kind of structure for graphs, but it was not very useful because we have no fixed node ordering. You cannot say that node. You can say when you draw the graph in the paper, you can say node 1, node 2, but actually in some other thing, if you say node 5 is node 1, that is actually okay, right? Because which one is actually node 1, which one is node 2, that is not there. So therefore, the problem with graphs is that there is no node ordering, and also it can have multiple features. So it can have various kind of multimodal features. Therefore, the traditional way of representing data does not work for graphs, and therefore we will have we need this graph neural network. And that is what I think you will study next week in one or two classes. But I just wanted for people, a lot of people you already know of neural networks, but people you don't know, because all the things that we talked about, like once you have created the representation of the graph, then we have to have all these things that we talked about, is optimization, creating this gradient descent, all those things are applicable. But how you take the initial graph and create the structure, that is what is different in graph neural network, and you will study about that in a later class.